He went to Princeton, graduated, studied computer science, and he's been leading an integration with Quantopian into the curriculum of top-tier universities, MIT Sloan, Cornell, and I'm blanking on the last one, but
there's a lot now.
It's growing. He's traveling all over the world, so he was able to be here today. So welcome, Delaney.
Thank you. And I haven't done anything yet. It's patronizing. Thank you for coming to this session. I was buried against a few heavy-hitting names in the other sessions, but that's fine because I'm not an invited speaker, so it doesn't actually matter what I think about this session. What we're going to talk about today is basically just kind of a brief intro into our whole educational ecosystem that we have now in Quantopian, through the process of actually trying to teach some topics briefly. Obviously, in the space of 40 minutes, I'm not going to really have time to dig down, but all the materials that we see today are freely available online, and you can clone them into your own account with one click when you have a Quantopian account. So I'll show you what that means. First of all, like Brian was saying, my primary job is academic outreach, and the reason for this is because about a year ago now, we realized that we built all this stuff, right, which is the classic startup approach, which is you build cool stuff, users will come, and then question mark, and then profit. And we chose a quantitative investment firm where we would allocate up to users. Jess talked about that in her session as our profit model, our business model. And because now we want our users to be well educated, we want them to know what they're doing, we actually have kind of a reverse incentive compared to most other finance firms that have ever existed. So most other finance firms have had a strong anti-incentive to share any information or educate anybody. We have a strong incentive to share and educate. The other thing we realized is that a lot of professors teach this stuff. They have the same problem that everybody else does, which is that they can't get at the data, they don't have any infrastructure set up to run backtest or test algorithms. And we said, well, we can solve that problem for you because we have all that infrastructure pre-built, so why not just use us to teach in the classroom? And so a lot of professors started doing that. As a result, a lot of curriculum started getting developed. This is the result of that. All of these lectures are either directly taken from or inspired by or filling in the gaps of top-tier master's programs. So these, tier places like MIT Sloan, Cornell, Princeton, Harvard, all of these schools that would traditionally offer your Wall Street feeder master's programs. And we just took that curriculum and said, why don't we make it available on our website? There's nothing stopping us from doing that. And as an example, we're just going to dive into the first thing we're going to talk about today, which is overfitting. And like I said, if any of you want to follow along, that screen you saw there, that's available under quantopian.com/lectures. It's also available under help. And at any point, you can go to that website and get all of this content, as long as you have a Quantopian account. So this is, in our research environment, this is an IPython notebook. Are people here familiar with IPython notebooks? They're super, super popular now in both the academic world and industry. And to give you an idea of how powerful they are, I need to turn off this so I can actually go to a new tab. But to give you an idea of how powerful they are, anybody familiar with the recent discovery of gravitational waves? I figure many people in this room would be. They actually took all of their analysis and put it into these IPython notebooks. So you can actually reproduce the experiment, or at least the data processing component of the experiment, to discover gravitational waves. And they give you this notebook, and you can see it has all of the introductions of why it exists, where the data is coming from, how to download the data, how to import it into the notebooks, what statistics you're going to run on the data, what plots you're going to generate. You can go through all the same analysis they did at LIGO. And so we basically take the same format and put it into our lectures. And so these lectures are combinations of text and plots and all sorts of fun, useful stuff. I'll just quickly go ahead and we're going to briefly cruise through 2 lectures today. Again, very limited time frame, so the goal is more to give you some key concepts, but also give you the ability to kind of learn this more on your own. So, overfitting. Who here is familiar with overfitting? How to avoid overfitting? Who here has ever overfitted? Okay, this is good. A lot of times I say that, nobody raises their hands, and I don't know if because they're shy or they actually believe they have an overfit. Of course, as you all know, everybody overfits all the time. Humans kind of overfit like it's our job. It's kind of a flaw in the human psychology because humans evolved in a very stationary world. Emmanuel Durman touched on this in his talk this morning. We evolved in a world where every lion we saw behaved pretty much exactly the same as the previous lion we saw. Every red berry tasted exactly the same as the other red berry, right? It's very stationary. Things don't change. Finance is the opposite. Finance is a very non-stationary, moving target. Things change very quickly. It's a complex system. And for anybody who's studied chaos theory, you know that basically there's a fundamental difference between complex systems and stationary systems. And so a lot of the techniques that classical statistics has been developed on and our brain has been developed on work for stationary systems like large populations and on heights and IQ scores and that kind of stuff, but doesn't really make sense when you apply it to financial markets. And so one of the big things that I talk about all the time when I'm going around the world is just that there's actually a tremendous misunderstanding because a ton of statistics have been developed with a bunch of assumptions being made. And it turns out those assumptions are just completely flagrantly violated on financial data. And so we're going to run through a few of them today. So first of all, overfitting. I'm not going to run through this super simple example. This is an example I have in here for people who have literally never heard of the concept of overfitting before, and I have to somehow explain it in a way that's manageable. We'll jump straight to curve fitting. This is a classic example of overfitting. Here I just have some x points, and then y is quadratically dependent on x, so x squared. That's my function in my data is y equals x squared, but plus some noise because no data comes without noise. And I fit 3 models to it. I fit a linear model, a quadratic model, and a 9-dimensional polynomial. Did anybody remember their high school algebra? How many roots does a 9-dimensional polynomial have? It's got 10 roots, basically 10 degrees of freedom, 10 parameters, and 10 points, so fits perfectly. And the important point, of course, is that no quadratic function will ever fit this perfectly. And so you see a tremendous amount of overfitting in finance because as you add parameters to your model, it's going to increase the fit because you're going to be able to explain more of your data. Whether or not that explanation is just spurious or actually truly, related to the underlying model, it's almost impossible to know most of the time. And there's a tremendous amount, and again, Emmanuel Durman touched on this, there's a tremendous amount of overcomplication of models in finance because people seem to think that that simple models are bad because you're not trying hard enough, right? Or that complex models sell better sometimes. If you can walk into a room and be like, we have this stats whiz kids straight out of MIT, and they've implemented a deep learning neural net that's going to mine the price data, price movements out of the S&P 500. You're already starting at a shooting yourself in the foot scenario. It's just so common. And a lot of it is just because people don't realize that they're doing it. And so, yeah, basically, in general, you want to keep your number of parameters low. You want to beware of the perfect fit because all real data has noise. The perfect model will actually rarely be 100% accurate. And you don't know what percentage of your data set is noise, so you don't actually know when to stop, right? Like, maybe the perfect model is 40% accurate and the rest of your data is just garbage. And you're explaining 50% of your data, and you're like, this isn't very good, I'm only explaining 50% of my data, I want to explain 80% of my data. There's just no way to do that, right? Another example, regression parameters. This is, again, run through this quickly because I think the next one's going to be a little more interesting. Regression parameters, you can see here we have a regression model, and I'll make this a little bigger. You have a regression model, and we're going to look at two models to predict the price of PG. We're going to have one in which the price of PG depends on PEP, and one in which the price of PG depends on all these 4 symbols that we put into our model. And so you can see Well, if we run this over the years 2013 to 2014, the R squared, the adjusted R squared of the single linear regression with one independent variable is 72. So you can think of it, it explains 72% of the prices. And then the adjusted R squared of the other one is 82. So it explains 10% more of the prices. And again, if you're not being careful, if you're not checking what's going on, if you're not reading the write-up of whatever model you're being handed, that might naively seem better. And a surprising percentage of the time, people do go for the more accurate model just because it's more accurate. In practice, you have to be very, very careful about doing this because what we've done here is, and again, this was not contrived. You can try this with kind of any symbols you want. You can try this with any time period you want. What's happening here is, in a linear regression model, if you add another independent variable, and that independent variable has no relationship with your dependent variable, the linear regression will just set the coefficient of that independent variable to 0. It won't use it. So it won't hurt the accuracy. If there is any kind of spurious relationship with the dependent variable, something based completely on random chance, it will set the coefficient to something that's not 0 and increase the accuracy. So your accuracy upon adding parameters, and this is not just true for regression, it's true in general, every time you add a parameter, you'll generally get a more accurate model. And that's why it's so tempting and so dangerous, because oftentimes people forget what adding parameters means, right? Adding parameters is literally just adding any kind of extra complexity to your model. Any kind of tweaking, any kind of small change that adds a little bit of complexity. You've added a parameter, and you will almost always get a better accuracy out of it. And the question, of course, is that accuracy real? Or is it just spurious, non-meaningful correlations in your data? And you can see here that if we run this over the next year, the single linear regression model actually maintains a reasonable explanatory power. You have a 42% rate of data that's been explained. So definitely not as good. There's still, it was overfit to some noise in the first year. But look at what happens to the multiple linear regression model. It goes down to 0. No explanatory power. So in adding those 3 extra parameters, you've completely destroyed your predictive power out of sample, even though in sample it's more accurate. Again, this is just like, regression is used so much in finance, and this is just, it's right here. You add parameters, you destroy your regression ability to predict anything out of sample. So I see this done a lot. And this is a fun one. Has anybody used moving averages in their strategies? Has anybody, how do you pick a moving average window in general? This is entrapment, by the way. Just look at a lot of values.
Yeah, it's a parameter. Yeah. How long window to pick?
Sure, it's a parameter. So a lot of people will try to optimize, and a lot of people don't know the difference between optimization and robust optimization, or fuzzy optimization as it's sometimes known. This is just moving averages on a stock, and here's a simple function that's meant to basically do a scientific study. This isn't actually a trading strategy. What this does is it says, given a stock and a window length, just do a simple mean reversion strategy where you look at the last n days, say, is my current price more than 1 standard deviation above the last n days, more than 1 standard deviation below the last n days? If so, trade in the opposite direction, and just count how many units of money you would have made, right? So the important point here is that this is a monotonic rating. It's not telling you the exact percentage return or anything. It's just saying, give me a way to figure out what is the best window length. So here, we look at 2013 to 2015, and 2011 to 2013, and we look at all window lengths in a range of 1 to 255, and the best length is 11. Okay? I mean, that's what the data says. So we're going to look at over the next 2 years. Any predictions? Will this prediction hold? What will the real window length be over the next 2 years? By the way, I also didn't doctor this data. Random stock. I picked a completely random stock for this. This is not contrived. Again, you can try this on like any example you want. It'll probably turn out pretty similarly. So the important thing that I'm going to do is I'm going to plot two curves. One of them is in blue. You can see the first 2 years and each window length and how much it makes you. In green is the next 2 years and each window length and how much it makes you. This is overfit, just a little bit. And of course, in practice, the best one over the next 2 years is just a really long one. And that also is pretty good in the first 2 years as well, but you just missed it because of this. So this is a classic problem of over-optimization. In practice, it's very risky to optimize, and optimization is like, it's like, I don't know, statistical techniques, oftentimes people make analogies to weapons. Optimization is like a rocket launcher. Like, you will probably kill yourself without proper training and optimization. And the thing I like to say is that quant finance is the only subject that I know of. Only subject that I know of in which the quality of your statistics is directly linked to the balance of your bank account. So you have to be careful. Because if you over-optimize and you aren't aware of, that you've over-optimized because it's subtle, because you've like added a parameter or you've tried 10 values and you pick the best one, you can completely, you can think you're going to make a lot of money and in reality be in for a really bad shock. So optimization in general is difficult. Again, there's some tips here for like avoiding overfitting. Out-of-sample testing is really the only way to do this. There are some ways to kind of increase your odds during an out-of-sample test, which are, say, things like cross-validation information criterion, which I would encourage you to look at in your own time if you're curious. But out-of-sample testing is really the only gold standard way to try to minimize your risk of being overfit. And what that means is that when you start the problem, you take a set of your data, you put it in the safe, you just do not look at it. I really mean that. You just don't even look at it because the brain is too good at interpreting trends quickly, right? You do not look at it, and then once you're done, you've generated a model, you're like super sure it's right, you run it on the out-of-sample data, you see what its predictive power is on that data, because that's data you haven't seen before, you can't be overfit to it because you haven't used it in the development of your model, and you see if the accuracies hold up in the out-of-sample data. And a super common mistake, one that like has famously made its way into peer-published, peer-reviewed research before, is people who do this, but then they say, well, my model didn't work in my out-of-sample test. People see where this is going. My model didn't work in my out-of-sample test, so my boss still needs a model, so I'm going to go back and train another model in the in-sample data and then test again in the out-of-sample data. That's no longer out-of-sample data because you've tested on it once, you've incorporated information about it into the new model. There's all sorts of reasons why that's not good. And in practice, you either have to hold out many chunks of out-of-sample data or just wait for new out-of-sample data to come in. And if you can't do that, you just cannot be sure your model is, reasonable, basically. And this is just a disclaimer that in case anybody at some point during this presentation was under the weird assumption that this constituted any kind of like investment advice, it does not. Hooray, compliance. And the next thing we're going to talk about, and then I'll open it up for any questions people might have. The next thing I'm going to talk about is violation of regression models, because regression models have somehow become like the only thing that's ever used in professional finance a lot of the time. They are really the core of arbitrage pricing theory and factor modeling, and they're just used to estimate parameters in every which way. So something I want to briefly talk about is like, let's look at some ways in which regression models can be wrong. Well, the regression model statistics that you're looking at are reporting that they're right. Because that's the bad case, right? If you think your model's wrong, that's fine. You're not going to trade it. If you think your model is right and it's not, that's the bad case. And so that's why the title of this talk is You Don't Know How Wrong You Are. And basically trying to look at hidden biases, things that can cause you to be wrong without even knowing or suspecting that you might be wrong. So one really important technique is residuals analysis. Are people familiar with residuals analysis? It's super common in statistics. It basically says, oftentimes models are very hard to analyze. They can be complicated, they can be nonlinear. Sometimes you can't derive maximum likelihood functions or anything nice, any of those nice things that statisticians like, mathematicians like. So rather than analyzing the model, analyze the error of the model's predictions. So you have some historical data, you have the model, you say, make predictions, and then see what actually happened. The difference between the two is the residuals, also known as the error, identical terms. So residual analysis is saying, analyze the residuals to gain information about the underlying model. Super common technique. So here's a few ways in which you can know that things are not super cool in your model. Everybody familiar with normal distributions? Nothing in finance is normally distributed, by the way. And I mean like nothing. I teach workshops, and I'll mention that at the end. I teach workshops, and oftentimes what I do as a challenge in the workshops is I'll give people 20 minutes to find anything, any financial data set they can that passes a statistical normality test. And they have yet to do so in any of my workshops. So basically nothing in finance is normally distributed. If you read the fine print of the vast majority of statistical tests and data analytics methods, at some point in the little fine print it says, this works assuming your data are normally distributed, or this works assuming your residuals are normally distributed. So if they're not, that goes out the window. That's why econometrics exists. Econometrics and time series statistics are basically correcting for that and applying all sorts of corrections to classical statistics in the presence of non-normality, in the presence of non-stationary variance, all sorts of weird stuff. So that's why that exists as a field. So, testing for normality. Well, friendly statisticians have already written tests for us, so we don't have to worry about that. Of course, whenever you pull up a new test, it's a little hard to see here, but whenever you pull up a new test, one thing that I always like to do is just run it on sample data so I can see which direction the test goes, because your p-values can be big or large, and you don't know if that means that you should accept the hypothesis or reject the hypothesis. So here we just say, generate some normal data, run our normality test on it, generate some non-normal data, run a normality test on it. Looks like this test, if it's below a cutoff, we ping as non-normal. So from now on, we'll say, let's have a 5% p-value cutoff, and then anytime our p-values fall below 5%, we say, this data probably not normal. You got to pick your cutoffs in advance, by the way. If you don't pick your cutoffs in advance, I will be sad. You will lose money. This is a super common problem, especially in academia. People just do not pick cutoffs in advance, and they'll get a p-value. They won't pick a cutoff, and then they'll get a p-value of 10 to the negative fifth, and be like, oh my god, this is significant at 10 to the negative fourth. That's wrong for so many reasons that I don't have time to explain today. Just trust that your friendly local neighborhood statistician has spent hours making sure that if you follow this precise set of directions, you'll be okay. So follow that precise set of directions, and those directions are pick a p-value cutoff, run the test on your data, check if it's above or below the cutoff. It's binary, that's it. Accept, reject. So, testing for normality of residuals is really important, and we'll see a few examples of how that will catch us. Are people here familiar with heteroscedasticity? Homoscedasticity? I would hope both or none. This is a really common topic. It's this is your statistician's fanny pack 5 top tools type thing. What you do is you say, let's look at a model and let's look at the actual points. So here are actual points, and then here's a model we drew through them. You can see here, this is a great model. This is a linear relationship in our points. This gets it pretty right almost all the time. Very low error. But the other important point is that not only is it very low error, it's very nicely distributed error. There's no structure of the error. It's just random, right? Like, it's kind of like, pick this point. How far away from this point should I expect the error, like the real value to be? Well, the error is the same here as it is here, as it is here. That's homoscedasticity. Homo meaning same. So this is, your error is the same the whole way through. This is nice. This is what you want, okay? What you don't want is something like this. You can see here that the magnitude of the error is actually dependent on an independent variable. This is very bad. This is known as heteroscedasticity, because it means that the error is not uniformly distributed. It's dependent on something else. This is known as having structure in your residuals, which means that the way I like to say it is you're leaving something on the table, right? So the idea here is that if your residuals are not just kind of uniformly or normally distributed, there's some structure in there, but your model was supposed to explain all the structure of your data, but some of it's being left over in the residuals, so you're clearly doing something wrong. So in this case, your model is not accounting for some structure, and the structure is showing itself in the residuals. Make sense? That's heteroscedasticity. And again, there's tests for this. These are just kind of the standard regression output tables that are popped out. We're not going to go into like reading these a lot, but the important point to know here is that even in the case of heteroscedasticity, oftentimes the p-values are otherwise known as the f-test. So in this case, this is the f-test of the nice case. But oftentimes the p-values of the f-test can come back as significant, right? So you ask the question, is this linear regression predictive? And the linear regression p-value will see like, yes, it is predictive. All your statistics look fine. But in reality, you're just not going to have very good predictions. So that's an example of how your statistics can cover up problems in your residuals. Here's just some tests you can do for heteroscedasticity. It looks like the test that's designed for heteroscedasticity catches it, and the normality test catches it. Great, 2 for 1. I say normality test is like your best fire alarm, and you should just be constantly testing everything you're doing for normality. That's what I do. Just like anytime I see a piece of data, I'm like, is it normal? Because if not, I need to do some work. There's also corrections for it. One of the important key points here is that in the presence of any kind of weirdness in your data, your computations of variance are going to be wrong. Variance assumes certain things. And so if your computations of variance are wrong, p-values, right, or standard error is based on variance. Because you say a standard error is like the parameter's variance away from the mean estimate. It could be in that range. That's the standard error bar of the parameter estimate. And the same thing for p-values. They say when you're testing if two populations are different, you say, here's one, here's the variance, here's one, here's the variance, do they overlap or not? If your variance estimates are wrong, then your p-values and your standard errors will be wrong. So if you're trying to use p-values as an estimate of like, are you right, you're just going to be completely wrong in the presence of things like heteroscedasticity and non-normality. Here's another big one. This is autocorrelation. Serial correlation. Everything in finance is autocorrelated. Pretty much everything. Everything except like 2 things. But just it's there. And the reason for that is because current conditions are taken into account when people make decisions that affect future conditions. And the definition of autocorrelation is when information from time t minus 1 affects time t. Believe it or not, classical statistics does not account for any kind of this. It deals with unordered sets, populations that don't have a time dimension. As soon as you add a time dimension, you have the ability for one time point to influence the next time point. That leads to autocorrelation. So here's an example of, this is just a symbol. And like you might try to estimate the trend of this symbol with a regression line. But what you're seeing here is this is like a textbook example of autocorrelation. In an autocorrelated series, because information at time t minus 1 affects time t, ups tend to lead to more ups, downs tend to lead to more downs, and you get much spikier data. Make sense? So that's what's happening here. You see just huge spikes that you would just never expect to see in like nicely distributed data. And we can test that. Here are 2 tests, and these are just running and looking at, for 1 bar before, 2 bars before, 3 bars before, is that price predictive of this price? So what is the correlation between the current price and the price 1 bar before, the price 2 bars before, the price 3 bars before? You can see massive amounts of predictiveness and many lags back in this data.
You're not actually testing the prices, you're testing the returns.
In this case, I am actually testing the prices here.
But they're bound to correlate.
Sure, they are. But it's just be aware of that in the case like, what if you're dealing with something like pairs trading, which is actually running regressions over prices? Yeah, just again, you have to be aware of the cases in which this will happen, and you also should check returns. Here, we'll also check the residuals. Residuals here, massively, still autocorrelated because you haven't explained any of the autocorrelation in your data. You've just tried to fit a line to it, which leaves all the autocorrelation on the table. So yeah, the approach to this would normally be trying to do basically kind of what's known as detrending, which is looking 1 level down and saying, let's look at the returns or the derivative of the price series. And then Nui West is a correction that actually tries to correct your variance estimates in the presence of autocorrelation. So this is another one of those econometrics time series analysis corrections that were developed to deal with this. And then the final example here is multicollinearity, which is just something else I wanted to address. This is just a super simple one. This is when one variable is highly correlated with another independent variable, right? So 2 independent variables highly correlated. If that's the case, because they're highly correlated, they both really explain the same stuff. So the regression can equivalently assign like 1, 0, 0.5, 0.5, 0, 1, doesn't matter. So you're going to get super unstable estimates in your regression if your independent variables are correlated. And this is just another super common thing, because oftentimes things in finance are very correlated. And if you try to use 2 of them to predict one other thing, then they're going to be super correlated, and your regressions just won't make any sense. So it's just another example of a way that you can dig yourself into a hole. That's all I have time to do for today. I wanted to leave a few minutes for questions, but before I take questions, I wanted to say one more thing, which is, I don't know if any of you are coming to the workshop tomorrow. We're having a workshop. It's sold out, so like this is me offering wine I don't have in my house. But I wanted to make you guys aware that we do these. If you go to quantopian.com/workshops, you'll see them. I just got back from 3 in Asia Pacific region. Again, holding one tomorrow. And these workshops are full day interactive sessions where we alternate between going through lectures like this and then actually doing exercises on your own machines, which means, like in your Quantopian platform, you clone the lecture, you play with it, I give you exercises, you try to develop some of your own stuff. And we always have Quantopian, at least myself, sometimes other Quantopian employees there to help if you get stuck and need to debug or whatnot. So we run those all around the place. They're fun. I get to travel. But again, like I said, I appreciate people coming to this because we were up against some heavy hitters. So what I do want to do is, again, like I said, the one tomorrow is sold out, but I will give a random person who came to this talk a free ticket to a future one, reimbursable. The tickets normally go for $700. I'll give you a free ticket. If you can make it, obviously, it has to be that I can run a workshop near where you are. A free ticket, and to get into the running for that free ticket, either tweet at me, that's preferable. I'll give you like 2 entries if you tweet at me. This is shameless self-promotion. Tweet at me, or if you don't have Twitter and you hate Twitter, you can email me, which I'll give you 1 point in the entries, and then I'll do a proper roulette wheel selection, and I'll select out someone from that pile and get back to you and let you know that you have gotten the free ticket. Anyway, that's all I had.
When Addresses to.
Email address, yeah.
Well, see, that's a good question. You had to figure that one out, actually.
That's the trick.
That's the trick. No, it's at the street quant, like the street quant, and I have no idea how that was not taken already on Twitter, but it's mine now. So I've been like tweeting all day, like at Quantopian stuff about QuantCon, so it should be pretty easy to figure out that it's me. All right, so we have, I think, a few minutes for.
Email address.
This is good. No, this is actually good because I deliberately don't say it because I want to know, do people actually care, right? Email address is Delaney@Quantopian. Delaney, my first name, Delaney, and it's just @Quantopian. It's also like, if you just search me, I'm sure you'll find it. Google's pretty.
Just the about page.
The about page does have it, Brian. Where is it?
Quantopian/about.
Did we take out the reference to it? I think we might have taken out the reference in the one, yeah. That's me. Actually, if you GitHub connect with me in some way, I'll give you like 3 points. That would be impressive. I don't even know like if GitHub supports social media interaction, but if you figure out a way, that'll go a long way. Did anybody have any questions, comments, concerns about any of this stuff? Again, all of this material is available online. If you go to Help Lectures, you can get any of the stuff we talked about today and any of the stuff that we didn't talk about today. Tomorrow in the workshop, in case you wanted to read the lectures on your own time, we're going to be dealing with the factor modeling lectures and talking about long-short portfolios and estimating risk exposure and all that fun stuff. Yes?
Quick question. When you test your models, do you use any theory like differential equations or maybe stochastic differential equations?
So I would say that those type of things would be tools for building a model, because you set up a model using, stochastic calculus or using differential equations. And then the tools to test a model usually fall pretty heavily into the realm of statistics and model validation. So there would be like, I've used differential equations to make some predictions, and then I'm going to test those predictions using like residuals analysis. At least that's usually what's done.
Okay, but maybe I should reformulate my question. When you feed one set of data and it works, and then you feed another set of data into your model and it doesn't work, how do you know which one is correct and which one is correct to feed and which one is not correct to feed?
So you're talking about different time periods, because sometimes in that case, like let's say you fed in your in-sample data and it worked, and then your out-of-sample data and it didn't work, or vice versa, then I wouldn't say that either data is correct to feed, I would just say that your model is wrong.
Okay,
it's not a good model,
what if
basically.
You build a momentum model, and
sure.
then you feed the mean reverting price series into it.
Sure.
And it doesn't work. It doesn't mean your model is bad, it means that data is not applicable.
Well, I mean, okay, so like refer back to what Emmanuel Derman was talking about, right? A model is a theory, right? And theories stand on their own. And theories can explain how the world works well, or theories can just not explain how the world works well. And the world changes. So some theories that used to work in finance no longer work. Some theories that didn't used to work now work in finance. And so different kinds of models go in and out of predictive power. And models are basically, they're known as having life cycles. And in general, what tends to be the case is if you have any suspicion that a model that isn't working, like just move on and try to find another model. Because it's just not necessarily worth your time. Because oftentimes if a model doesn't work on the first try, all you'll end up doing is like tweaking it, overfitting it, changing parameters, adding parameters. You're not necessarily adding anything new to your insights, right? And I think in general, the hallmark of a good model is one that like you spend hours slaving away, you have like 7 failed tries, and all of a sudden you realize, oh wait, this was how this should be working, and then it works on the first try, right? Rarely is it the case that your model like doesn't work on the first try, so you like tweak it, you feed another data set, that's generally the neighborhood in which you're over optimizing and you're looking at potential for overfitting. Any other questions? Anybody coming to the workshop tomorrow? Cool. I'm assuming that a lot of people coming to the workshop tomorrow was like, I don't want to hear his talk twice. So they, which is fair. That's very fair.
Okay, thank you.
All right, thanks for coming, guys.